Hello students, welcome back. So now we are going to talk about the simulation generation. And in this video, we are going to focus on that what is behavior simulation before the synthesis, the concept of different types of waveform generation, how can we generate all possible test cases without mentioning them one by one, and the precautions that need to be taken while analyzing these waveforms. So let us get started. So behavior simulation is very critical to test the functionality of your given digital system. Using these waveform, we can test each and every individual input test case, whether my system is performing as per the user specification or not. Behavior simulation is also used to test the functionality at different stages as well. It is not only the final system that we can test, we can also test it in phase-wise manner as well. We can generate these input waveforms and create the test cases and test whichever component we want at a given time. So how do we generate these waveforms? Various types of signals can be assigned to these input signals. We can have constants like binary number, hexadecimal, decimal, and then we can also give them clock values. Clock is always going up and down, 0 and 1, with a given frequency and duty cycle. So let us get started on Vivado and understand all these terms. So here we are in Vivado and I have my simulation source which is set as full adder. That means there will be 3 inputs and 2 outputs. There can be additional signals also. Now let us see how can we generate these input cases. So we go to simulation and run simulation and we say run behavior simulation. So now it is going to prepare the simulation environment, and here what we have already learned that you should always give access to Vivado. Now here we have A, B, C in. So now we have allocated the inputs to all the 3 values. We can check the simulations. In hexadecimal or binary or octal, in all of them 0 will have the same magnitude, and that is 0. 1 will also have the same. So right now we can ignore and select either binary or hexadecimal and say OK. We are going to allocate a certain constant value to B as well, and I have allocated 1. And similarly we allocate another constant to C in, and now we can see that this is one test case. If I have to get all the cases, that means 8 cases, I have to repeat this 8 times. Then we take the concept of generating clocks. So now let me show you. I say force clock. So leading edge and trailing edge. Leading means high, trailing means low. So 1 and 0, it will start with the simulation and duty cycle. So duty cycle is the amount of time for which the wave is high. 50% means the waveform will have 50% uptime, 50% downtime. If you say 70% and my total duration is period is 100 nanosecond, that means for 70 nanosecond the wave will be high value and for 30 nanosecond it will be low. If I say duty cycle is 10% for the same time period, then it will be high only for 10 nanoseconds, and for the remaining 90 nanoseconds it will be low. So by default we keep it this and we say OK. So my wave is defined for a period of 100 nanosecond, and I am running the simulation for 800 nanosecond here. I run this simulation and then I expand it, and here we say zoom fit. Now you can see this is 1, 2, 3, 4, 5, 6, 7 and 8. It started with 1, high, low, 8 waveforms in 800 nanosecond are generated, and you can think them as 10101010. So now you are getting an idea that when we write the truth table, the least significant bit is 101010. The next one is 0011 0011 0011, and the next one is 4 times 0 4 times 1 4 times 0 4 times 1, and the next higher one will be 8 times 0 8 times 1. So how do I generate a waveform which will have 2021s now? Well, the logic is simple. Just make the time period as double, and for the next one 4 times, and the next one 8 times. So let us try that. So I go to B and I say force clock again 1 and 0, and here I say time period 200, and for C in force clock 1 0 and time period 400, and I run it again for 800 nanoseconds. We expand it and zoom fit and see here. Let me zoom it. Here we got those waveforms. This is the first one, the upper one, 1010. This is 1100 1100 if you look only for this much time. And the next one is 1111. For 4 values it is 1, and for next 4 values it is 0. So you can see all the cases are generated. 111 011 101 001 110 010 100 000. All the cases are generated, but they are not in the sequence like 0002 111. For that, what we should do, we should give the clock starting with a 0. Okay, starting with a 0 we should give. So now I give a clock here 0 to 1 with 200 nanosecond and 0 to 1 with 400 nanosecond, and we run the simulation again and we see that what is the output now. We zoom it and let us zoom slightly on this side, and here now you will see this is 000 001 010 011, then 100 101 110 and 111. This is one very important aspect, generating all possible test cases. How do we do it? Now let us come to one more simulation that I want to show you regarding the hexadecimal, decimal and signed numbers. For that, I am going to go back to my sources. I have already made one adder for 4-bit addition. We are going to discuss that in our next module, but for demo purpose, I am just showing you the simulation. So I set it as my top module in the design as well as the simulation sources, and let me prepare the simulation for that. So here what do we have? I have 4 bits of A. You can expand it to check. Then I have 4 bits of B and 1 bit of C, total 9 inputs. total input cases will be 2 raised to power 9, 5, 1, 2. It will be very large simulation, very difficult to read manually. So in these cases, what we do, we normally test some of the cases individually, manually, and remaining we do it by scripting or by the waveform generation. So here I say force constant now. This is hexadecimal, and if I write 5 here, this will be hexadecimal number 5. My B is, I'm going to say force constant, and let us say 4, and C in, it is a single bit value, so I cannot write 2 or 3 here. Okay, it should be a binary number 0 or 1. Okay, let me keep it 0. Now I am going to run this simulation for a brief period of 100 nanosecond, and you can see 5 plus 4 plus 0, answer is 9. Let me take one more case. Here I say my hexadecimal number is A. A is basically 10, right? So it is going to be 5 plus 10, 15. Okay, we are expecting 15, and that is what we got, F. F is 15. Let me try one more case, and here I say instead of 5 I take 9. So 9 plus 10 is 19. Okay, and when I run it, what I got is 3. But Cout is 1. Cout 1 means 16 numbers are taken as carry. So 16 plus 3 is 19. Now let us look at these in a completely different way. So here is what you can do. Right click on this and say radix. Default radix will show you the best possible value, but you can say no, I want to see binary format, so it will show you binary format. You can say I want to see hexadecimal or ASCII or unsigned decimal value. So here my answers are 9, F and 3. Here I go to radix and say unsigned decimal. So now you can see it is 9 and this is 15. Okay, this is A. I go there and say unsigned decimal. So 5 plus 10 is 15. 9 plus 10 is 3 plus carry is 1. That means 16 plus 3, 19. So this is the concept of radix. Please select the radix appropriately as per your convenience or leave it as default, whichever you like. So here what we can do, we can allocate constants, we can allocate clocks, and when it comes to the simulation waveform, then we can select the radix. There is one common problem that we observe, and let me show you what is that issue. Let me just give a waveform here, just some random waveform I am giving with 100 nanosecond, and I run this for 100 microsecond. Okay, that means 1000 simulations are run, and when I see it is all filled up, and then you are confused, nothing is visible, all the waveforms are all filled up. Basically in this small window there are 1000 simulations, they are cramped up. To see them you need to zoom out and keep zooming out until you see them. This problem will definitely come when you will simulate counters and similar circuits. Please be aware when you do that. So students, now we have a good idea about simulations and waveform generation as well. We'll come back to the Verilog concepts and learn about Verilog assignments in our next video. Keep learning. Thank you.